In July 1969, human beings successfully landed on the moon. It is the defining story of the space race, and usually it's where the story ends in our collective memory. But the first landing was technically messy. For the entire duration of their descent down to the lunar surface, Neil Armstrong and Buzz Aldrin were flying miles off course. They eventually touched down in a random, unplanned location. Surviving the drop was a massive engineering victory, but for NASA's scientific goals, guessing where you might park on the moon was unsustainable. Targeted geological research requires a level of landing precision that Apollo 11 simply didn't have. To solve that problem, NASA launched 6 more crewed lunar landings in the 3 years following that first step. Apollo 11 proved that humans could survive the trip. The missions that followed were a compressed, frantic sprint to master the hostile lunar environment. Apollo 12 launched just months later with a specific mandate: prove NASA could pull off a pinpoint landing. To test this, they aimed for the Surveyor 3 spacecraft, a robotic probe that had been sitting on the moon since 1967. The pressure from Washington was immense. President Nixon and his wife had traveled to Florida to watch the launch in person, and NASA knew if they scrubbed the mission, they would lose months of momentum. They decided to launch in the middle of a thunderstorm. This meant flying a highly volatile 36-story Saturn V rocket directly into a dark, electrically charged sky. At an altitude of 6,000 feet, Apollo 12 was struck by lightning. Warning lights illuminated every panel in the cockpit. 16 seconds later, at 14,000 feet, they were struck again. The spacecraft lost its main power supply and its navigation systems while accelerating at an incredible speed. The crew was seconds away from a fatal abort when a flight controller on the ground remembered a similar electrical failure from a training simulation. He radioed up an obscure command: try SCE to aux. Flipping that single switch restored auxiliary power, saving the entire mission. After surviving the launch, Apollo 12 executed a near-perfect descent. They landed right on the edge of the target crater, just 180 meters away from the Surveyor 3 probe. They proved precision was possible, but the margin for error remained razor-thin. Just a few months later, an oxygen tank exploded aboard Apollo 13 halfway to the moon, forcing the crew into a desperate fight for their lives. These back-to-back incidents showed that simply arriving at the moon required an exhausting level of crisis management before any science could even begin. To get the program back on track, NASA called up Alan Shepard to command Apollo 14. At 47 years old, he was the oldest astronaut in the program, bringing decades of critical flight experience. That experience was immediately necessary. En route to the moon, the command module failed to latch onto the lunar lander. The crew attempted the electronic docking maneuver 6 separate times and failed each time. Without that connection, they couldn't land. Shepard turned off the electronic docking probe and successfully flew the capsule manually, eyeballing the alignment to save the mission. He piloted Apollo 14 to the most accurate touchdown yet, just 87 feet from their target. On the surface, he attached the head of a 6-iron to a lunar sampling tool and awkwardly swung with one arm, sending a golf ball flying across the low-gravity landscape. That specific combination of mechanical skill and public levity restored confidence in NASA's landing capabilities. They had survived the learning curve, clearing the path for a scientific upgrade. Apollo 15 expanded the mission window. An upgraded life support system allowed the crew to live on the surface for 3 full days. They also brought the Lunar Roving Vehicle, a battery-powered electric dune buggy. This gave the crew the ability to drive across dozens of kilometers of alien terrain on a single charge. This expanded range led directly to the collection of the Genesis rock, a piece of the moon's crust dating back 4.1 billion years to the very formation of our solar system. 10 months later, Apollo 16 used their rover to target the lunar highlands. Scientists on Earth had hypothesized that this rugged region was the site of ancient volcanic activity. The crew's physical investigation revealed the opposite. The highlands had been smashed from above by massive asteroid impacts, which pushed the terrain into its current form. Astronauts were now operating as active field researchers, directly rewriting our understanding of how the moon's geography formed. This scientific ambition peaked in December 1972 with Apollo 17. Every previous astronaut to walk on the moon had been a jet pilot. Harrison Schmitt was a professional geologist. The scope of the mission was record-breaking. Schmidt and his commander spent 75 hours on the surface, driving their rover over 36 kilometers away from the safety of their landing site. Using his trained eye, Schmidt noticed something unusual beneath the standard gray dust. He uncovered bright orange soil, which was later identified as volcanic glass spheres formed 3.6 billion years ago. In total, the Apollo 17 crew loaded 110 kilograms of individual rock and soil samples back into their spacecraft, the largest physical haul of any lunar mission. As they prepared to leave, Mission Commander Eugene Cernan stepped onto the ladder. He would become the last human being to stand on the moon, signing off with a message of peace and hope for all mankind. The data returned from these missions revealed a complex active history of the moon. These samples provided the specific chemical signatures needed to map the early volcanic history of our solar system. In the span of 3 volatile years, NASA successfully targeted, landed, and recovered 6 different crews. They evolved their operations from survival mechanics to precise geological research, a hyper-concentrated burst of scientific evolution that remains unmatched.